Hello everyone, welcome back to the channel. In today's session, we will explore an important topic in microcontroller programming. Lecture 7, Arithmetic Instructions in the 8051 microcontroller. Today's topic of the day focuses on how the microcontroller performs mathematical operations like addition, subtraction, incremental and decremental. In this lecture, we will cover three main aspects. First of all, the syntax of arithmetic instructions. We will understand how instructions like add, ADD, subtraction, SUBB, incremental INC, decremental DEC are written and used in programs. Secondly, the working of arithmetic instructions. We will see how these operations are executed internally using registers like the accumulator A, and how flags like carry flag and overflow flag are affected. Okay. Third, we will discuss the application of arithmetic instructions, where these operations are used in real programs such as counters, calculations, data processing, and embedded system tasks. By the end of this lecture, you will clearly understand how arithmetic operations are performed inside the microcontroller and how to use them effectively in your programs. So let's get started. Okay. So now we come on this today's topic, arithmetic instructions. We will cover these topics in today's presentation. Syntax of arithmetic instructions, working of arithmetic instructions, applications of arithmetic instructions. We will see one by one of these subtopics. Now, first of all, we will see the recap on the data transfer instructions. We have already discussed these part. First of all, instruction set basics and types. We have already studied, right? Second thing, data transfer instructions, that is immediate, register and internal memory. Next, data transfer instructions to access stack. Already we have seen in the previous lecture. Last one, data transfer instructions to access program memory and external data memory. Also we have seen in the previous lecture. Now, after this presentation, you will learn these things. First of all, identify and use basic arithmetic instructions in 8051 assembly programming. Right? Next, understanding working and how flags are affected by arithmetic operations. Right? Last thing, apply arithmetic instructions to perform calculations in embedded applications. Okay? Now, we will see the one by one of each instructions. Okay? So, first of all, we will see the arithmetic instructions. The instructions are given in this column, right? Addition ADD, addition with carry ADDC, subtraction SUBB, subtraction with borrow, also use this instruction, right? Incremental purpose, that is the INC. Increment in the using A accumulator and using the DPTR. Okay. Next thing, decremental DEC, we will use this instruction, right? MUL, multiplication, right? We will see also how to multiply these things. Division, DIV, right? DIV, right? So we will see these things, and DA also, this is the. Now we are just discussing of all the instructions one by one, right? So first of all, we will see the addition instruction, right? For this addition, suppose we want to add two numbers, right? So how to add two numbers? So we can use this instruction ADD A comma R1, right? This instruction is used for the addition of two numbers. Okay, this instruction is a 1 byte instruction, remember, and this instruction is executed by one machine cycle, right? Suppose we want to use this instruction, so we can put op code, right? Operation code we can use in the hexadecimal 29, right? If we want to add two numbers but also provide the carry, so we can use this instruction ADDC A comma has 25H. Okay. So after this addition, the carry 1 is generated, right? For this, this instruction is a 2 byte instruction, right? This instruction will be executed by one machine cycle, right? For this, we can use the opcode 94, right? That is not a 94, you can just speak in this way 9425H. Okay? Okay. Now, for the subtraction purpose, SUBB, that is the instruction for subtraction, right? So subtraction SUBB A comma R naught, right? For this instruction is a 1 byte instruction, and it will be executed by one machine cycle, remember, right? The opcode of this instruction is 28, right? What is the use of opcode? We have already seen in the previous lecture. If you not done the previous lecture, so first of all you see the previous lecture, right? Incremental instruction. So INC instruction we can use here for the incremental purpose, right? So INCA, incremental accumulator, okay? This instruction is also 1 byte instruction, right? This instruction will be executed by one machine cycle, right? So for the opcode purpose, you can use here 04H, right? Suppose we want to use incremental DPTR. So this is also the 1 byte instruction, but two machine cycles are required for executing of this instruction. Remember, right? Operation code for this instruction is A3, right? Suppose you want to use the operation code A3, that means you want to use this instruction in the program, right? Next thing, decremental 50H. This is the just location of the memory, right? This instruction is a 2-byte instruction, right? For this execution by 2 cycles, right? The opcode of this 1550H. Remember, right? For the multiplication, right? So we can use here the instruction as example MULAB. Remember, not a comma here, directly multiply this A into B, AB, right? So this instruction is 1 byte instruction, and execution of this instruction is required the 4 cycle of this, right? The opcode, that is the A4 for this, right? For the division, instruction for division DIV, right? Example of this instruction is DIV AB. Okay, noted. This instruction is a 1 byte instruction, right? The execution of this instruction by the 2 cycles. So we can say 4 cycles are required for execution of this instruction. Remember? Okay. Opcode number is A84H, right? You can use this opcode also, right, for execution of this instruction. Next one, that is the DA. DA, that is the decimal adjustment, right? Here this instruction is decimal adjustment accumulator. Suppose this instruction is a 1 byte instruction. The execution of this instruction by the 1 cycle, right? The opcode of this D4. Suppose you want to use the opcode D4, that means you can use this instruction, right? Now we can move for the next slide, right? Arithmetic instruction. First of all, we will see the add, that is the addition. Add the instruction we can use for the addition purpose. Okay, so we can take a syntax here. Add a comma source. Okay, we can use here, right? So one by one we will see. This source is nothing but we can use here the register, memory, immediate number also we can use here. Next thing, operation of this add instruction. C by carry A plus source. Remember, right? A plus source. A, that is the accumulator, plus source. This is the thing, okay, of this addition instruction. Now we can take a small example. You see here, right? So now we can take a small number. This number is the FF number. This is the hexadecimal number. Now we can represent here. This number is the binary number of this hexadecimal number, right? Second number is the 11H. That is the hexadecimal number. This hexadecimal number is converted into the binary number. You can see here, this is the binary number of the 11H. Okay, okay. Now we want to add these two binary numbers. Okay, so 1 plus 1, right, that is the 0. 1 carry, this is 1. 1 plus 0 1 plus 1 0, this one carry 1, right, this one. 1 plus 0 plus 1 0 carry 1, right, this one. 1 plus 1 0 carry 1, that is this one. 1 plus 1 0 plus 1 1 carry 1, right. 1 plus 0 plus 1 0 carry 1. 1 plus 0 plus 1 0, right, carry 1. 1 plus 0 plus 1 0 carry 1. Okay, okay. Now we want to just we have calculated this number is the addition number, this one, है this is the 8 digit carry, this is the 9 number digit. Okay, okay. Now we want to store this result in the accumulator, right. This result will be stored in the accumulator, this one. This is the carry, right, this one. Now we want to see which bit is affect, right, in this calculation. Okay, so here we can see here carry, auxiliary carry, parity flag, overflow flag. Okay, so first of all we can see here overflow flag is 0 because this number is not a signed number. That means overflow flag is 0. 1 is finished, right? This is not affected, noted. Okay, then you can see how many ones is given here, right? Only 1. That means this is the odd number. Okay, if the total number of ones are odd, that means parity flag is 1. That means parity flag is set. Okay, okay. Next thing we will see the auxiliary carry. This flag is set or reset, right? How to define this auxiliary carry flag? Okay, basically this carry is generated from the last digit of the lower nibble. Okay, this one. This is the basically thing of this lower nibble you see here, and this one. This is the 4 digit. This is the 4 digit, right? Total 8 digit. But this is the lower nibble. This is the higher nibble we can distribute in this form, right? Suppose carry generated from last digit of this to this. That means auxiliary carry flag will set. Okay, and in the similar way the carry flag is set or reset if carry is generated from the last digit of the byte, है ना? This one. That means carry flag is set. Noted? Okay. In this way we can calculate, right? Now we can take another example here. ADC, addition with carry, right? This thing. This is, you remember, this is ADC is nothing but this is the A double D C. Remember, okay, this is the correction. You just correct of this, right? Now we can just a solve of this A double DC addition with carry. We can use this syntax A comma source. In the similar way, we will see here, you see, right? Source is nothing but this should be the register, memory or immediate number, right? We can take a small example here, you can see, right? This is the A plus source plus carry, right? In this example, carry will generate it and store in the another register. Okay, noted. In the previous example, we have ignore the carry digit, right? Only the answer we have stored in the accumulator, right? But in this case, we can store the carry in the another register. Remember, right? For the incremental purpose, the INC you see here, this is the INC instruction. Syntax of this INC destination. Destination is nothing but this should be the register or memory. Okay. Here not use the immediate number. Remember, right? For example, INC are not, okay, INC 50H, okay, INC at the rate are not. In this way, we can represent the syntax of the incremental right instruction. Okay. Now we will see the subtraction with borrow, right? Can also here do some correction. Borrow, this is not spelling is okay. Borrow, B-O, right? You correct this also. The small mistakes are there. Syntax of this SUBB A comma source, right? Source is nothing but register, memory, immediate number as the previous, right? Operation carry, or we can just put here the just a borrow. In this case, this should be the borrow, right? A minus source minus borrow, right? This is the thing of the operation of subtraction. Take the 2's complement of the subtrahend, right? First number. Second number, add it to the minuend accumulator, right? Third thing, invert the carry, right? For example, we can take example here 01H minus 02H, right? This is the small question. Now we can solve this question step by step, right? You can see here, we can take a small example. You see, this is the 02H, right? This one. We can represent this number in the binary form, okay? So two number we can represent the binary in this way, 0100, right? Second thing, 0, this is the 0, all zeros, right? This is the binary number. Second thing, right? First of all, when we will calculate the number of this in this way, right? This is the 2's complement, basically you see here, right? This is the numbers 1, 0, this is the first complement, right? This one is the first complement of this, है ना? 0 1 1 0 0 1 0 1 0 1 0 1. He converted 0 to 1 or 1 to 0. That is the first complement, right? After that, we can use this one as an addition, right? That means this solution is called the 2's complement, right? So 2's complement after the addition of this number, right? The result will come in this way. right? You can see the carry is not generated. You see here, carry is not generated. This number is the F, this number is the E, FE, right? This is the minus 2D, right? This thing. So this is the negative values come here. Now we come on the 0, 1 value, right? This one. The 0, 1 value we can represent in this way, right? Where this is the way of choose just binary number of this hexadecimal number, right? In the same way, we can calculate here, you see, 2's complement already we have solved here. Now we can, right? This is the minus 2, right? This is the 0, 1 value, right? This is minus 2 value. This is the 0, 1 value. Now we can add of this number, right? Now the calculation of this, suppose the result of this is not, carry is not generated in the last digit of this, right, byte. That's why this number is called the, just a negative number, right? So this is the FF, right? Now we can solve here, you can see this is the thing, right? Now we will solve the decremental, right? Syntax of decremental is DEC and destination, okay? So destination is nothing but register or memory. We can use any one here. INC R0, INC 50, right? INC at the rate R0, right? In this way, just we can put in the similar way, we can use the decremental also. Decremental is nothing but in the same case we can use here. We can try to complete of this syntax for the decremental, right? DEC, and that is the destination, right? Destination, this one. So destination is nothing but we can put here the register or memory. In this way we can calculate in this way DEC and R0, or we can use also DEC and 50H. In this way we can represent, or also in this way we can represent, right? This is the R0, right? So we can solve, right, by using this method, right? Now we come on the syntax multiply AB, right? MULAB, right? Now we come on this calculation. Operation of this, you see here, A multiply B. The result should become in the AB. First digit will come here in the accumulator A. If more digits available in the result, they will come in the B register. Okay? Noted? Yes. Now we can take a small example here, right? A, that is the 1H, B, that is the 2H. Write the multiply of these two numbers, right? So that number is the 24002H, right? So remember this 42 digit, and we can take a small example, or we can just summarize this thing. Right. You see here this number, right? This number and this number, 8 digit, right? So this value is stored in this register A and this value is stored in the register B. Okay, remember? Okay. Now we can move for the next overflow flag 1 if V register is having non-zero result. Okay, noted? Okay. Now we can start the DIVAB, that is the division instruction, right? So A, that is the quotient, B, that is the remainder, right? A divided by B. So we can calculate in this way. A, that is the 10H, B, that is the 03H. The instruction we can use here DIVAB, right? The accumulator register will be stored in the accumulator, that is the 05, and the remainder that will be given here, the 01 in the B register. Overflow flag 1 if V register is 00. Remember? Okay? Okay. In the similar way, we will see here the decimal adjustment, right? Accumulator. So this instruction is beneficial for the BCD number, right? So you see here after an add instruction or a double DEC instruction, if the lower nibble, right, 4 bits is greater than 9 number, noted, right? Or if AC equal to 1, right? AC equal to 1. So add 0110 to the lower 4 bits. Remember? Okay. Next thing, for this instruction, the second condition is if the upper nibble, this is lower nibble, right? This is upper nibble, is greater than 9. Here the greater than 9 in the nibble, here the greater than 9 or carry should be 1. Right? This is the same thing. Add 0110 to the upper 4 bits. है ना? So first of all we calculate the nibble, right? Lower nibble and higher nibble. If these conditions are fulfilled, so we can add the 6 value. 0110 is nothing but 6 number in BCD form, right? Okay. So we can take a small example here. Hexadecimal value, that is the 29. The BCD number that is given here. This one. This is the 9 number, or this is the 2 number, that is the 29 number. Right? We can add here, you see. Right? Add here this one. Plus 18 hexadecimal number. Now result is given here. 41. Right? You can see here the carry generated or not generated. Carry generated from here in the nibble side. Right? So 06 should be added here. Here not carry generated. That means here not use the 6 value. Here 6 value should be added. Right? You see here. We can add this X value. The final answer is 47. Understood? Okay. Now we can move for the summary of today's presentation. Right? So in this session we have discussed, right, following key topics: syntax of arithmetic instruction, working of arithmetic instruction, application of arithmetic instructions, right? In the next lecture, we will explore how logical instructions help the 8051 make decisions, mask bits, and control hardware conditions efficiently. Right? Some sample questions also given here. Right? You can solve these questions and provide the answer in the comment box. I will see and I will check also. Right? In embedded systems, arithmetic instructions are not just about numbers, they are how a microcontroller makes real world decisions, one calculation at a time. Thank you very much for listening me.